Hello everybody. Today we're going to be learning partial fraction decomposition, commonly referred to as PFD. Partial fraction decomposition is an algebraic transformation of a fraction into its parts. Why do we need to learn partial fraction decomposition? Well, in reality, partial fraction decomposition can come up quite frequently when doing integral calculus. Additionally, it allows us to take a complex fraction and simplify it into something that's more manageable for the mathematician. So, what does partial fraction decomposition actually look like? We'll start with a simple example. Say we're given the expression 2 over x minus 2 plus 3 over x minus 1. If we wanted to add these two fractions so that we could rewrite this as one fraction, we would have to find a common denominator between the two pieces and then add the numerators. Let me go ahead and demonstrate how that's completed. Now that these fractions have the same denominator, we can simply add the tops. First, notice that we distribute the values. Then, we're allowed to combine like terms. That gives us 5x minus 8 over x minus 2 times x minus 1. Partial fraction decomposition allows us to complete this problem, but in reverse. That is to go from our final answer here to the initial answer we had here. Now that we know what we're doing, let's jump into a problem. Let's try to rewrite 5x minus 4 divided by x squared minus x minus 2 as a partial fraction. First, notice that the denominator here can actually be factored into x minus 2 times x plus 1. Now, using the conventional tools of algebra, we can't really get any further with this problem. But partial fraction decomposition suggests that we can actually rewrite this as the sum of two partial fractions, a divided by x minus 2 plus b divided by x plus 1. Notice here that the placement of a and b are actually arbitrarily defined, and we could flip these in whatever order we want. Now the next thing that we're going to want to do is solve for a and b. To do this, we might want to simplify the fraction on the left-hand side. To do that, we can actually multiply both sides of the equation by this denominator here so that we get 5x minus 4 is equal to a times x plus 1 plus b times x minus 2. Then we have a much simpler equation with only one missing variable. So there are many approaches to solving this, but the first approach that you should take is to try and plug in the roots of a and b. The root of a is given by solving x plus 1 equals 0, which lets us observe that x is equal to negative 1. To get the root of b, we solve x minus 2 is equal to 0, which gives us x is equal to 2. Okay, let's start by plugging this first root in. So if we plug in x is equal to negative 1, we should get 5 times negative 1, which is negative 5, minus 4 is equal to a times negative 1 plus 1, which is 0, plus b times negative 1 minus negative 2, which is negative 3. Simplifying this gives us negative 9 is equal to negative 3b. Now, solving for b, we find that b is equal to 3. Okay, now we just need to solve for a. Let's try and plug in the other root and see if it allows us to. So if we plug in 2, we get 5 times 2, which is equal to 10, minus 4 is equal to a times 2 plus 1, which is equal to 3, plus b times 2 minus 2, which is equal to 0. This simplifies to 6 is equal to 3a. Solving for a tells us that a is equal to 2. Now, we can plug in the values of a and b up here where we started, and it should give us the correct partial fraction. 2 divided by x minus 2 plus 3 divided by x plus 1. And there we have it. We solved our first partial fraction. Now let's try and move into some more complicated examples. This next problem is going to require us to be a little more careful. Let's try to rewrite 10x plus 35 over x plus 4 squared as a partial fraction. The natural idea here might be to rewrite this as 10x plus 35 over x plus 4 times x plus 4. But partial fraction decomposition actually allows us to start from here and put this fraction into its proper form. So let me show you the appropriate form for decomposing this fraction. Here the appropriate form is going to be a over x plus 4 plus b over x plus 4 squared. In fact, this works regardless of the exponent in the denominator. Let's go ahead and try and solve for a and b here. So if we use the same trick to simplify this expression as we did last time, we would get 10x plus 35 is equal to a times x plus 4 plus b. Notice here that, well, b doesn't really have a root that we can solve for, but we can go ahead and solve for the root of a. Just like we did last time, x plus 4 equal to 0 gives us the root x is equal to negative 4. Then we can try and plug in negative 4. That would give us 10 times negative 4, which is negative 40, plus 35 is equal to a times negative 4 plus 4, which is 0, plus b. This simplifies to negative 5 is equal to b, giving us b. Now let's go ahead and try and choose an x such that we can solve for a. Notice here, because b has no x and we know what b is, we can go ahead and write that into our equation. So why don't we replace b with negative 5. Now that b is replaced by a number, it might be easier to see that if we can choose any value of x that doesn't make this part of our expression equal to 0, and that will solve for a. So why don't we select an easy one and just let x equal 0. If we let x equal 0, then we have 10 times 0, which is 0, plus 35 is equal to a times 0 plus 4, which is just 4a, minus 5. If we go ahead and solve for a, then we should get 40 is equal to 4a. Then 10 is equal to a. Finally, we have a and b, and we can come back up here and rewrite our fraction as the sum of its partial fractions. That will give us 10 over x plus 4 plus negative 5 over x plus 4 squared. Finally, let's finish this video with an even more difficult problem. Let's try and rewrite 3x squared plus 7x plus 28 divided by x cubed plus x squared plus 7x as a partial fraction. The first thing to note is the bottom can be simplified. We can pull an x out of this sum and rewrite it as x squared plus x plus 7, which gives us something a little bit more manageable. But here we need to learn a new form to the partial fraction decomposition to rewrite this. If, for instance, one of the parts of our denominator contains an x squared, then we need to write the top as, in this case, bx plus c. Let me demonstrate the form here. Rewriting this, we would get a over x plus bx plus c over x squared plus x plus 7. Now let's simplify this in the same way that we've simplified before. We'll rewrite it as x squared plus 7x plus 28 is equal to a times x squared plus x plus 7 plus bx plus c multiplied by x. This expression is much more intimidating to solve than anything that we've done before. However, let's apply some basic principles of algebra to see if we can get this into a much more manageable form. Let's distribute the a first to get ax squared plus ax plus 7a. Then we can distribute this x over here so that we get bx squared plus cx, and the left-hand side remains the same. Now, using some intuition, we can group like terms, ax squared plus bx squared plus ax plus cx plus 7a. Then we can pull the x squared out in front of this expression, and we can pull the x out in front of this expression. So that we have 3x squared plus 7x plus 28 is equal to x squared times a plus b plus x times a plus c plus 7a. Now that we've written it in this way, and we want it to equal this side of the equation, we have a much simpler problem. We want the coefficient of the x squared over here to equal a plus b, which is multiplied by the x squared over here. So we get a plus b must be equal to 3. Additionally, we apply the same principle over here to a plus c and 7x, and we find that a plus c must equal 7. Now, the only problem is to find each of these parts individually. What we can do is pick an x such that these sums are canceled out. The appropriate x here would be 0, since 0 times a plus b is 0, and 0 times a plus c is 0, which would leave us only with the 7a, and would help us to solve this problem. So if we plug in 0, we get 3 times 0 squared, which is 0, plus 7 times 0, which is 0, plus 28 is equal to, as we discussed, 7a. If we divide this out appropriately, we solve for a, and we get a is equal to 4. Now that we know a is equal to 4, we have 4 plus b is equal to 3, and 4 plus c is equal to 7. Solving for b and c here gives you b is equal to -1, and c is equal to 3. Now we've solved this more complicated problem and can rewrite the partial fraction here as 4 over x plus -x plus 3 divided by x squared plus x plus 7. And if you doubt this answer, you can actually, like we did in the first and introductory example, multiply to get a common denominator and actually add these, and you should come back to the original fraction we started with. Now that we've gone over a few of the basic partial fraction decompositions you might encounter, I want to give you a set of rules that will help you identify the proper form to apply when decomposing a fraction. The first rule is going to be if we have some denominator that can be factored and is of the form x plus 3 times x plus 4. This is the denominator for our first example, and it gives us a over x plus 3 plus b over x plus 4. Another denominator we can encounter, which we did encounter in the second example, is a denominator of the form x plus 3 squared. This can be rewritten as a over x plus 3 plus b over x plus 3 squared. And then similar to problem 3, if we have a denominator that looks of the form x squared plus x plus 17, which is an unfactorable expression or polynomial, then the form of our PFD will be ax plus b over x squared plus x plus 17. Note that these forms only apply when you have a proper fraction, not an improper fraction. If you have a higher order polynomial on the top than you do on the bottom, first you'll need to apply polynomial long division, and then these rules will start to apply again. Okay? Thank you for learning partial fraction decomposition with us today. All of these problems come from Paul's online math notes. I'll go ahead and link that in the description below. Paul's online math notes is a great resource for anybody trying to learn algebra or calculus, as it has plenty of examples and thorough descriptions of the mathematics behind solving these more complicated problems. Finally, if you like this video, go ahead and click the subscribe button and leave comments for future videos on topics that you'd like covered. Thank you.